we see things because of the light, but the ideally light is electromagnetic wave. So electromagnetic waves first explain electromagnetism by Maxwell's theory around 1860, more than 200 years ago. So the Maxwell discovered that when there is a electric field and the magnetic field, if there is an electric field and the magnetic field oscillating and then moving together, that can actually generate what we call the electromagnetic waves. So the idea is this, what he discovered. So if I have electric field which oscillates, this is, let's consider x-axis, y-axis, z-axis. If I have electric field oscillating, look like a sinusoidal wave function, look like that on xy plane. And then if there is a magnetic field oscillating perpendicular to that, look like this on xz plane. So these two can create a single quantity and then simultaneously move one direction. Now this motion direction is on x, E field is on y, B field is on z axis, and the propagation direction is actually x direction. So that's actually what we nowadays call the electromagnetic waves. So all the energy in the observable universe, now everybody I think in generally know observable universe and the universe model, this Big Bang model and things like that. So if you take a look, all the energies in the universe, you can understand all the energies in electromagnetic spectrum. So if I take a look at the electromagnetic spectrum, so that has very high energy radiation, which we generally call the gamma, like the radiation type we use to treat some cancers and then so on. Then we have X-rays, which generally used to take the X-ray pictures and then so on. And then we have the UVs, ultraviolets. All of these are very high energy usually, okay? Usually not good for human health. And then right here, in the middle of the spectrum, we have a region, very, very small, tiny region called the visible spectrum. Visible spectrum means what we can see, technically what human can see. So that visible spectrum contain all the colors. So usually purple color, dark purple, dark blue, and then so on all the way to red here. Okay, all of those colors generally we consider the spectrum colors which we can observe. By putting all the spectrum colors together, then we have the white color. White is not just a color, it actually contains all the spectrum colors together. Okay. And then on this side, we have low energy part, infrared region, and then we have here microwaves, and then below here we have radio waves, TV waves, and then all the other mobile communication, and then things like that. All of these are very low energies. So these are very low energy region. This is very, very high energy region. High energy is not good, but there are a lot of application on them. Low energy is totally fine for humans, nothing going to be happen. A lot of application on that region too. And then infrared is very unique on electromagnetic spectrum. The infrared means anything burning gonna emit some sort of radiation, which means for example, if you take a look any animal, including the human beings, if you eat something, we burn those things inside our furnace, and then we get the energy by burning the what we eat. So any human being or any animal who burning the food to actually maintain the body temperature usually emits amount of radiation. So that radiation is actually go under the IR region. So that's why the night vision cameras actually can be produced, which means if you have a camera which can detect IR region, IR radiation, then if you look at the night outside, then none of the other non-living things not emitting the IR, which means any other inorganic things like the trees and things like that, not emitting IRs. But if there's a human or animal who actually burning and then keep maintain the body temperature, emits the IR. So then we can easily detect the organic creatures, and then out of the organic creatures, different creatures can separate it out within the temperature of that particular object. Then we can identify whether it's a human being or different animal, and then so on. You can see how much this electromagnetic spectrum is so uniquely connected to almost like everything we do in our day-to-day life. Mobile communication, TV communication, thing to the medical application, X-rays and the gamma rays, and then so on. So other than the visible region, you can see how much it is really important. So that's one of the most important discovery is actually understanding the electromagnetic spectrum to the whole development of the engineering and application. Okay. So out of that, what we interested today only visible, which means what we can see. So if I consider the visible light, which we can see, what we're going to try to understand how we actually see things. The human eye itself can actually respond to the visible region of the light. So which means how the human eye basically see things. We're not going to go detail into the lenses and mirrors today. There are different properties when it comes to the observing things. We're going to take a look two important properties under that. So we're going to take a look how we see things under reflection and the refraction. So the reflection means when the light rays bouncing back to the same side. So the light ray idea means now you know visible light is actually 3D electromagnetic wave. Okay, technically it should be a 3D electromagnetic wave, but we're not gonna treat it like that. We're gonna consider only the propagation direction of that wave. Because of that, if I want to understand these two properties of the light, I can draw propagation direction of the light. So we basically drawing ray diagrams. Ray diagrams means we basically drawing the line with the arrow. That line is actually the wave itself, but that arrow represents the propagation direction of the wave. Okay, so we don't need to draw the wave always, because the three-dimensional wave, what we interested only that propagation direction of the light. Okay, by using that concept, we're going to understand these two particular properties of light. Because of that, generally this goes under geometric optics. Geometric optics means we're going to draw a diagram and then try to understand how we see things. Okay. All right. So let's take a look at the idea of the reflection. Any question? Okay, reflection means when the light passes through, if the light hits the surface, if that surface does not allow light to pass through to the other side, then light is going to be reflected back itself. So we'll draw this line right here, which is 90-degree line to the surface. This side, let's consider this is a mirror. This side will be mirror side. This side is just air. And then this line, which is 90-degree and 90-degree line to this mirror surface, is actually called the normal line or the normal axis. So let's now send the light ray exactly this point right here. Now that's the light ray. That is technically an electromagnetic wave, but we're not interested in wave nature now. Okay, so we're interested in the direction of motion. When light hit this point, since it is not allowed to pass through, it will reflect it back itself to the same side. Then if I measure these two angles, then we can identify this angle. We can say theta of incident, because this is the ray of incident. This is the ray of reflected. Then this is going to be theta of reflected. Now, if you're doing this in-person class, this is actually what you observe in technically. This is the top view. So how we do this in-person class, we're going to take graph paper and then place on the table. Then we're gonna put right here a small laser beam, usually red color laser beam. Then you switch on, and then you put a mirror right here. Then this blue line, you can actually observe directly in the top view. So that's what exactly you observe. And then we take the pencil and then draw these lines. This line slowly we draw along with the laser beam, and then this line also we draw along with the laser beam. Then you can use a protractor and then identify 90-degree, draw this line. Then by using the protractor, we can measure these two angles. By measuring them, we can confirm law of reflection. Theta incident should be equal to the theta reflected. So that's why it's just generally called the geometric optics. The reason we just basically observing what really happening and then draw this diagram, which we call the ray diagram. And then by using that, we can confirm these simple laws, okay, to understand this phenomena. So it's a really nice experiment if we can do in a real in-person class setting. That is our party, just confirming law of reflection. Any question, guys? Okay, then let's move into the law of refraction. So law of refraction is actually confirmed by the Snell. Because of that, generally it's called the Snell's law. Snell's law, that's a person's name. Okay, what he done? Now this is actually goes whenever the light pass through to the different medium, which means light hitting the transparent medium. Transparent medium means like the glass piece, or maybe you can consider water, and then so on, anything which allow light to pass through. Let's take a look what will happen. Now, if I have a surface right here, let's consider this side is a glass piece. Now, this is exactly how you're going to do this experiment if it is in-person setting. We're going to place a graph paper. Then we're going to place a glass piece on top of that. Then we bring our laser beam again and then switch on the laser beam. And when you switch on the laser beam, let's draw this line right here, 90-degree line to the surface, which is the normal axis. And then you switch on the laser beam and then send the light ray to exactly this particular point. If you do that, then you can see this is where light's supposed to go, right? If it's not happening anything at that boundary, this side is air, this side is glass. However, we can immediately realize that the light is actually bending when light passing through one medium to another. That bending nature happen because of the speed of the light changes from medium of air to medium of the glass. For example, you can think about the glass medium is much denser compared to the air, so it does not allow the light pass through with the same speed. So speed of the light inside there, which is about 2.99 times 10 to the 8 meter per second, which is one of the most important property came out from the Maxwell's theory. He's the first person who theoretically proposed the speed of any electromagnetic radiation. So he confirmed the E divided by B ratio is this number mathematically without any experiment more than around 250 years ago. Okay. Now, after that, it took about like 6 decades, roughly about 60 years to experimentally confirm this by using the light. That's why we generally call this is the speed of the light, because that is only what we can directly observe. But you know now electromagnetic spectrum has a lot of other radiation, okay? All of this radiation is actually traveling with about the same speed, because all of the radiation are in a way electromagnetic spectrum, electromagnetic waves, okay? All right, so that's why we generally call it a light speed, and then that's the number anything can move in generally the highest velocity. None of the materials cannot move beyond that speed. If anything reaching that speed, later Einstein explained that everything gonna go into in some sort of energy. The matter cannot exist if the speed is come closer to this number or reach that number at all. Okay, so that's why we call that is ultimate speed. Nothing can pass through beyond that. Okay. All right, now this is speed gonna be changing if I have a different medium. The speed of the light inside there gonna be about that speed, and the speed inside the glass gonna be different. That's gonna be definitely much less compared to the speed of the sea. That letter C are using here. The reason the speed of the light usually use that letter C to represent. Okay, that's why. Now, what the Snell figure out is actually interesting. So Snell figure out some sort of correlation between this angle. If I measure the incident angle, all of this angle measured from the normal axis to the light ray itself. Okay, from the normal axis to the light ray. This angle, this is the incident light. This is going to be the incident angle. This is going to be the refracted light. Now it is not reflected, refracted light passing through to the next medium. If I measure this angle, that's going to be theta of Re, but now it is refracted. Okay, we are interested here. Refraction, reflection means come back to the same side. Okay, now geometrically he confirmed that sine of these two angles correlates with the refractive index of each medium. So let's quickly take a look. What is the idea of index of refraction or refractive index? Sometimes it's called index of refraction, depending on the textbook or the instructor. Sometimes it also called just the refractive index. Nothing wrong. What that means, what that refractive index or index of refraction means, it explains how the light is speed inside that particular medium relative to the speed of the light, ultimate speed of the light, or the maximum speed of the light. Which means if I take the ratio ultimate speed of the light divided by the speed of the light inside certain medium, that ratio is actually defined as this index. It's unitless, but it always greater than 1, because the reason V always less than C. So usually if I have a medium of air, then I will get N equal 1, because it basically C divided by C. It cancels out to 1. But if I have a medium like, let's say, for example, glass, then N is about 1.5, which means the light is speed inside that medium much less compared to the ultimate speed of the light. If I have a water, this number is about 1.33. If I have a diamond, then if you let the light pass through the diamond index of refraction is about 2.4. That about the highest refractive index most of the time we can see in application perspective. That is the reason you can see inside the diamond, the speed of the light V is very, very small. It is smaller than 50% of the ultimate speed. Okay, so that's the idea of refractive index. So which means what the Snell figure out, if we take the correlation between the refractive index of the medium 1 and then sine angle of the medium 1, which is air in this particular case, where the light comes in, that magnitude should be equal to the refractive index of the medium 2 times the sine of theta 2. This is actually in this particular case can be glass or either water in our experiment. Okay. Now light passing through medium air to medium glass or medium water. If that happens, this magnitude must remain the same. He confirmed this by just using the trigonometric diagram. Okay, that's why this usually called the geometric optics. Now that's our second part of the experiment. By using that Snell's law, or we can say the law of refraction, we can find index of refraction of the medium N2, which is equal N1 times sine theta 1 over sine theta 2. N1, which is equal to 1 because that is a medium of air. Because of that medium of the glass or water, we can calculate just by using angle sine theta 1 over sine theta 2. I just need the ray diagram. If I draw this ray diagram right here, this is now the top view. You're going to see if it is an in-person experiment. Then I can really draw these rays. Okay, we can really see this red color list. Then by taking the pencil, I can draw all those lines. By using the protractor, we can actually find these angles. Directly, we can measure them. By measuring them, we can actually take the sine of those angles and then calculate refractive index of the glass or water. Then those numbers, we know those are already tabulated. Then we can compare our experimentally calculated numbers into the known values. Then that way we can confirm the law of reflection or the Snell's law. Okay, that's our experiment part B. That's the plan. Any question, guys? Any problems? Okay, then let's continue into the experiment. So in our experiment, first we're going to confirm the law of reflection, then we're going to confirm the law of refraction. Okay, that's the plan. So to do that, there is a simulator link on page number 2, very top right here. If you click on that, that will open this small simulator, phet.colorado.edu, and then you click on the last option called the More Tools. Then you will see a page look like this that has a laser beam right here. And then on the top, you can see it's a white color, which means AR right here. You can see it says medium is AR. Index of refraction for that medium is 1.0 because the speed of the light is same in there. Okay. And the next medium right here below it says now glass. We can change that medium by just click this up arrow. We'll change that into water. Now water index of refraction is 1.33 because light speed is about 30%, 37% reduced when it go to that medium. Okay. Then you switch on the laser beam by clicking this red dot right here. Then you can see light ray comes in, goes to the other medium. Then clearly you can see the bending nature. And part of the intensity you can see reflected back exactly this surface, which means this same ray diagram we can use to explain both reflection and the refraction. We don't need the mirror surface. This surface can actually do the both. Okay. And the incident angle you can see I can change from here to here. Then this dotted black line is the normal axis. Then only thing we need is actually this ray diagram and the protractor to measure the angle. If you click this yellow circle and then bring it here, align this black small line right here in the middle of the yellow circle to the dotted line and then crossing point with the horizontal line. If you do that, then I can measure incident angle from black dot 0 of protractor to this point right here, and the reflected angle 0 to this point right here, refracted angle 0 from here to this point right here. Then by using those, I can easily confirm both of the ideas which we wanted to confirm. That's the plan, guys. Any question, problems?
No.
Okay, then let's move on. Let's start with the small incident angle. I'm gonna measure. You can see the laser beam is little bit thicker, a red line. Because of that, I'm gonna consider this outer edge of the laser beam on one side, right here, and then same outer edge on right here. Okay. So you have to make sure this point right here align exactly with the black dotted line. If not, then I have a reading error on here. Okay. Now, if you look at the outer edge, this is 0, this is 5, this is 10, 15, 20, 25, 30, and then so on. This is exactly 10 degrees incident angle from dotted line to the red color line outer edge. You go to the other side, dotted line to the red color line outer edge, exactly 10. Incident angle, reflected angle, both must be same because that is the idea of law of reflection. Then you compare them. The PD is 0, but I'm going to write the function anyway, equal open bracket ABS, open brackets, difference between the numbers, divide by average between the numbers. Okay. It should be 0 because it's same, but we'll write the function anyway. Okay, question. All right, then let's take a look what's going to be happening if I increasing the incident angle. Okay, let's increase this into 20. Use the outer edge of the laser light. Then it's 20, right here it's exactly 20, no difference at all. And then we'll try with 30. Exactly 30 other side, no difference at all. Then try with 40. Exactly 40 on the other side, no difference at all. Then try with the 50. Incident angle, you can do more data, but it seems to be not meaningful because it always same incident and the reflected. That's the idea of law of reflection. Any question? Okay, then we'll take a picture of our simulator right here. Insert screenshot. Take a picture of this part, including all of these, and then we'll leave it right here. All right, then we'll move into law of refraction or Snell's law. Now, to confirm the Snell's law, we have to calculate the index of refraction or refractive index for the other medium by using angle of incident and angle of refracted, taking the sign of them. Okay. We'll use the same angles which we used earlier. We'll start with little bit low angle, like maybe 10 degrees. And then we'll slowly change that by each 10 degrees at a time. Again, I'm going to use the outer edge right here, which means outer edge right here, okay, on the other side. When you're measuring the refracted angle, you have to be careful because I can measure down to 1 degree. Right here, you can see each 10 degree divided by 10 small lines. So which means I can measure down to 0.5 degrees by estimating between the 1 degree line. Okay. So try to measure as accurate as possible this outer edge. This is 5, this is 10, this should be then 9, this should be 8, this should be like about 7.5. As accurate as possible. Okay. Let's calculate that. The refractive index. We know that's just the ratio of sine incident to the refracted. Sine command equal sine command, and the Excel can read only radians. Because of that, you have to give the radian command inside every single trig functions with the Excel calculation. And then the incident angle right here, close double brackets, divide by sine command again, and then radian command inside that, and then refracted angle on C number 22, close double brackets, hit enter. That exactly the number we expecting to be the refractive index of the water. Okay, 1.33. Write it down carefully. That function is so important. If you don't have that correctly, then you will not get the right answer. Okay. All right, guys. Question, problems.
Professor,
What's up?
does it have to be n at the end too? Does it have to be 1.33 when you do the refractive index?
That's depending on what number you have here. If you have 7.5, that should be exactly like that. If you read it to like 7.0, then it's going to be slightly different. Okay.
And is that okay?
Yeah, that's a reading error. That's fine, I think, because I try to estimate between these two lines. If you read it to 7.0, that's okay, I think. That will be the reading error. You can keep it.
Okay.
Okay, then let's check it out. This couple of different incident angles. Any other questions, problems? Okay, 20-degree incident. It seems to be refracted is about 15. Click and drag the calculation. Looks good. There's a little bit of error now. That's always a reading error. That's totally fine. Then let's check it out. Couple of different incident angle. How about 30? Incident angle 30. Then refracted angle is around 20, 25, 4, 3, about 22. And then so on. You can check maybe like two more incident angle values. Maybe 40. Refracted is about 29, and then maybe 50 incident angle. Refracted is about 35.
Wait,
Then click and drag this, then it will do the calculation automatically.
Professor,
What's up?
I get confused. When you're clicking on like let's say 50, where'd you get the 35?
You have to measure that from here the same way you're measuring for 10.
Okay,
You
so
measure right there.
all right, so you're not looking at the 50, you're just going to 35 and I don't understand how you get like 40 to 29.
You have to change this incident angle 10 by 10. At 10 right here, incident angle is 10. Then you measure this point right here, that is 7.5. Then you change the incident angle to 20. Then
Okay,
you
so we're
come
going
here, then you measure this point right here, that is 15. Then you go 30. Then you come here and then measure this point, 22. Then you go 40. Then you come this side, measure this point, 29. Then you go 50. Then you come this side, measure this point, that is 35.
Okay, all right, thank you.
All right, it's little bit of some point we have a little bit of error, but overall it seems to be around 1.3, 1.32, and then so on. So it looks good. We can do the same for the maybe glass medium. We can change the medium on the second medium right here. You can change into glass by clicking the up arrow. Then it change the color automatically. Glass medium index of refraction is 1.5. We can do the same thing again. Any question, problems? Okay, then let's do the measurement again. We'll start with the lower incident angle again, 10 degrees. Then let's measure the refracted. This is 5, this is 10, this should be 9, 8, 7, about 7. and then you do again the sine command equal sine command and radian command inside that, then incident angle E22 double brackets divide by sine command and the radian command inside that, which is the refracted angle F22 close double brackets, hit enter. 1.425. That because our reading error. If we can read more accurately, then we will get a more better answer. Okay, this is for the glass. Then we'll do the same thing again like we done earlier. We can change the incident angle, maybe a couple of other values, and then we can take a look. Because if our theory is true, this number should not change as a function of we changing in the incident angle. That number should be about the same. That's what we actually checking here by repeating the measurement again and again. Okay. All right, let's do maybe 20-degree incident. If you do 20-degree, I'm measuring to the outer edge right here on the red line, outer edge on the other side right here. 10, this is 15, 14, around 13. 13, then click and drag the calculation. That looks good. We expecting 1.5. First data point, I have a little bit of error, but the second point is very good. It's very close. And let's do a couple of more data. Do maybe 30. This is very close to 20. I'm going to read into maybe 19.5 and 40. This is exactly around 25. And then 50. This is on exactly 30. You can see now these numbers, I'm using same incident angles for both medium, but the refracted angle you can immediately find is not the same, different. That because medium is different, light speed inside the medium are actually different. Okay. Then you click and drag. Some data points very close to the number we expecting. First data point little bit off, that's okay. But overall, it is around 1.5. Question problems. Okay, since we have 5 data points, we calculated again and again for same value. Usually if we do that, we're gonna take the average, right? Let's do the average here, equal average command. And for glass, selecting all of these cells on the table 2, column G, you can take the average. Average value is very good. We expecting 1.5, we're getting about the same number. In for glass, in calculated average for glass. And then we'll do the same for water.
Wait, Professor,
Equal. Yeah, what's up?
when you do the average, you know, G22 colon G26, do you have to put the colon in?
Yes.
Okay.
Yeah, that's true. Not, otherwise, you will not get the calculation correctly.
Professor, can you show us how you fit the calculated average glass formula?
How I use it right here? Right here. Equal average. You can type the average word.
No, I got that. I mean, how do you paste it? How do you make it look like that?
Oh, how I paste it? You go here and then copy. And then before you paste it, click the escape button. Escape button on your keyboard, okay? Then you click anywhere you want to paste it. Then type whatever you want to type in CalAVG for glass. Then paste it. Okay. All right, same for the water, okay. Equal average, parenthesis open, D22 colon D26 close brackets. Now that very perfect, exactly the number we expecting. Glass, almost close, but there's a little bit of error. Then we'll compare with the known values. There's no units or anything. This is just a unitless parameter, okay. Equal open bracket ABS, open brackets, expected number for the glass 1.5 minus calculated value is on D number 34, close bracket, divide by 1.5, close bracket, multiply by 100. So error is really very low, 0.05. That is PE for glass. Then we'll do the same for PE for water. Questions? Any problems? PE calculation, don't click and drag, okay? Because if you do that, it will not calculate correctly because expected value for water is different. You may have to type again, okay? Equal open brackets, ABS open bracket, expected value for water 1.33 minus calculated value for water D number 35, close bracket, divide by 1.33, close bracket, multiply 100. You can see still there's a little bit of error, even though you see here exactly 1.33. The reason, if you increase the number of decimals, it's not exactly 1.33. It's slightly different, okay? That's why I would suggest to keep maybe 4 decimal for these two, only 2 decimal for the calculated percent error values, okay? PE for water. Okay, question, problems. All right, so that's about it. This lab is fairly very simple. Even we do in person, this is fairly very most simple lab actually to do. Let's quickly take a look a little bit of what remaining in the semester. This is the last day of the experiment. Then only you have to complete this lab final exam. That is nothing to do with your class final exam or anything, okay? That is according to the syllabus only for the lab exam. That is very easy, very simple lab. All the question has a little bit of calculation based on the calculation we do on this Excel sheet. You don't need to use the Excel calculation, particularly you can use a calculator. For example, now, if question asking from this lab, it will, for example, give you information like it will tell you, we have done a refractive index experiment, then we measured incident angle like 20 degrees, refracted angle like 50 degrees, then question will ask you what is the refractive index of water. That's it. Then you know you need to take the sine of these two angle ratio. That already everything is on the Excel sheet. You can even do the calculation with the Excel sheet, then nothing wrong, but for the exam it might be easier to do with the calculator. Okay, make sure you have a calculator before you start the exam. And this folder right now is not visible to you. It will open up December 1st week, okay? Saturday, I think December 4th. Let's take a look what that day is. I think it's December 4th, okay? Next weekend, there's no class. And then December 4th, Saturday, this folder will open up. It will open around 6 a.m. in the morning, keep remaining open until the midnight. You can do the exam anytime you like. When you click on the exam, when you go into the folder, this icon, when you click on the exam, you have only one trial, which means after you click on this icon, the timer will switch on and you have 2 hours to complete the exam. So which means you can't test and come back again. Make sure you have 2-hour period before you start the exam, okay? And then you have to finish within that sitting. There's only 10 question, all multiple choice. It's very simple. You don't need 2 hours. You probably need only half an hour, but I usually give 2 hours for the exam, okay? You can refer to the class calculation, class work, and this Excel sheet if you want to. That's okay, I think. That should be fine. And I will be online during the class time, Saturday, which means this time 10 a.m. to 12 a.m. If you're doing that particular time period, you can contact me directly through the Zoom. But if you take in the exam any other time, I'm not online. So you're going to be on your own. And then if something happens, I'm not responsible. Okay. So you can contact me only if you take in during that time. Otherwise, you will not get any reply, even you have any problems. Okay.
Professor?
All right, guys. Yeah.
This is our last lab class?
Yeah, this is the last lab class.
Oh.
Yeah.
Thank you so much.
And then next week there's no class, and then followed by following week you take in the exam on that Saturday. I would suggest everybody to do the exam during the regular class time. Then if you have any trouble, any problem, I will be online to help with, okay?
Okay, so we have the whole day to do the exam.
If you want to, you can take the exam any other time, yeah.
Okay, thank you so much.
Yeah, during that day, okay? All right, guys. Any other question, any problems?
Professor, when does the video, the recorded video come on again, please?
Within an hour or so should be available.
Okay, thank you so much.
Mm-hmm. That's right. You don't need to log in into the Zoom. That's December 4th, Saturday. If you have question, you can log in. Otherwise, you don't need to. All right, guys. So then we stop from here, and then good luck with everything. If you have any question about the exam during the regular class time, always reach out. Okay. All right.
Thank you, Professor.
Professor?
What's up?
Hi, I just have a question about when you would be grading lab report 7, because I did it, but I don't know like when you would get the grade out. I was just like wondering like a time span or frame or whatever.
It should be already graded. Take a look again.
7?
Mm-hmm.
Okay, thank you so much.
Yep.
All right, have a great one.
Yep.
Professor, I'm going to show you my screen so that you know what I'm talking about. So I have the formulas. It's just that fitting it in this cube, like I don't know how to do that.
Oh, you just click and drag to the right word, maybe 3. No, not that way. Just click on the middle of the cell.
Middle of the cell?
Yeah, then drag to the right word, maybe 3 or 4 cells. And then go to the alignment part and then click merge and center.
Oh, and then I saw what you did.
You need to click from here, number 37, come over there and then click there. And then,
oh, oh, that's so cool. Okay.
Okay.
I had no idea. This is the first class I've ever used Excel, and I learned so much.
Yeah, that's okay. That's just simple formatting. You can learn that.
Yeah, I like Excel a lot. I hope I use it more. I really hope I use it more. And so again for the exam, like you're saying that it's gonna say what we have to do.
That's right. Yeah. Question almost has all the information. It will tell you what kind of experiment that is, and you will easily realize where to look if you want to refer to the data sheet. But make sure you have everything okay during the exam.
Okay, so I'm gonna just go over like what we did and.
Yeah. That's the best way. At least like day before, like couple of hours before, you can like collect all the data sheet and then take a look all the calculation. Then you should be fine.
Okay, thank you. And then if anything, we can come and ask you. So
Yeah.
Thank you, Professor. Oh, so it's okay. So it's okay that it kind of looks wobbly like this. I don't know how to center it all.
Oh, that's okay. That's fine.
Okay. All right. Thank you, Professor. Have a good weekend.
Yeah, you too.
Bye-bye.
Professor?
Hello, what's up?
I just have a question about my data sheets for 9 and 10. So I got a 3.90, but I'm kind of confused because I did all of the calculations, but you said I didn't.
Did you show up all the Excel functions?
Yes, I'm looking at it right now, and I have
Oh.
every function like
All
in.
the Excel functions are there.
Yeah.
Let me take a look there.
Okay.
9 and 10.
Yes.
Okay. And Yelena, right?
No, Ariana Pagan.
Oh, okay. Yeah. We take a look there. Where's the Excel function? Did you include that into that area? Where's yellow color highlighted area? I don't see it.
Oh, wait, so the functions we have to paste?
Yeah, you have to paste it. That's
Would I
why.
be able to redo it?
This is not going to change anything. It's a
Okay.
small amount of point. Don't worry about too
So
much.
it's not like a bad grade?
No, because you have 2 extra point anyway from that introductory class, right? So that's going to cover up this.
Okay.
Yeah. So all the other data sheet you have 10 all the points, right? Only
Yeah.
this 2 you have that issue. Okay. So nothing much to worry. This will cover up with that extra point.
Because I have, I think, 4. I have 4 with the 3.9. So, and then the rest are 4 out of 4.
Yeah, then nothing much to worry. It's going to be very simple amount of point. You have 2 extra point from the that introductory lab. And because of that, I think it will cover up definitely. Yeah.
Okay.
Yeah. Okay.
All right. Thank you.
Yeah.
Hello? Hello?
Yeah, what's up?
Hi, Professor. I checked on the syllabus that there was no class today, so I just want to make sure that I did not miss the class or anything.
Say it again. There's no class today.
Yeah, on the lab schedule for the semester, today is the 20th, right?
Let me check that.
Yeah, because it says
We
no class.
We just finished the class.
Oh my God. Yeah, this is.
No, 20th, there's a class. Where are you checking really? Go to the begin here, then there is a table on there. You're checking somewhere else, I think.
Okay. Oh my God, I mistaken it. All right, got it.
There's no class next week.
So sorry. Yeah.
You can still do the data sheet by looking
I
into
will.
the video. Yeah.
Yeah, I'm gonna review the upload, the lecture.
Okay.
Thank you so
Yeah.
much.
Yeah, no problem.
Have a good day. Bye.
Yeah.